Today we're going to use the excellent invention of first Baron Kelvin, Lord Kelvin if you will. He was included in the House of Lords, the first scientist if I'm not mistaken. We're going to use that to test a bunch of resistances on things, and then we're going to talk about the differences in motors and what you can gain from resistance testing them. So first off in this video, I just wanted to do some random resistance tests on items. I'm using the Kelvin 4-wire method that we just told you about in a previous video. I have a DC power supply that can current control. I have it set to 1 amp. I currently have it set to 1 amp of current. And then we have ourselves a digital voltmeter that reads in millivolts. It needs to have millivolts to register really low resistance items. You could, if your power supply could push 10 amps, you could just push 10 amps through everything, probably get your leads really hot, and you wouldn't need as much resolution on your voltmeter, but this one has plenty of resolution, so we're just gonna use it, and we're gonna start from there. So, I'm gonna be safe, and I'm gonna hook my leads up to an item before I turn on the power. Totally safe. It's the safe way to do it. We're all about safety here. And this is being a pain in the butt, so I am going to connect these down here instead. There we go, outside leads. This is the stator from a Trailmaster Pro 2700 kV motor. And that's gonna be our first test. Trailmaster Pro, yep. 540, 2700 kV. Turn that on, turn this on. And as I explained in the previous video, since we're only passing 1 amp through it, when we get 1 millivolt, that means we have 1 milliohm of resistance. So here we go. We'll put that in view for you. All right, we are getting 14.9, so basically 15 milliohms it looks like. Boom. Test it once again. Yep, 15 milliohms. Nice and low. That's one reason why, even though being a 2-pole, that these motors did really well. As compared to other motors of the same kV, my 2-poles actually have a much lower resistance because we are not limited to wire size and all that kind of stuff. No racing rules for us. Let's see, what next? Let's do Revolver 2500 kV. It's a much smaller housing than the 2-pole. This is going to be a 10-pole version. Let's see what its resistance is. It's a little bit slower of a motor, and slower motors have higher resistance, all things equal. But when we change motor topology, that changes. And we're actually going to have to measure this through the entire wire leads, which in the previous video I showed you adds about a milliohm and a half to these. So I guess we could go apples to apples and have measured the 2-pole motor through the leads too, but we're gonna rock on. All right, let's see if I can get it to not slip off. A sharp, pointy thing on a round, slippery bullet plug is not the easiest. All right, there we go. All right, so we are at 9.5 milliohms for this motor, for this Revolver V2 2500. Come on now. Just need to get it on there without it slipping. Yep, 9.5 milliohms, including the wire itself. 2 wires, actually. And I've got an extra wire that is already disconnected on this motor, and we can see what the resistance of the wire is, and then subtract that. Woo! Little sparky spark, low resistance wire. And we can subtract that from that measurement that we just got, the 9.5. Let's see, this is showing 2 milliohms. I don't know if I guess I should believe my equipment, but 2 milliohms seems a little high for this length of wire, although it is not the biggest. Cool. So this guy has a really low resistance. That's what I can tell you. Let's change the setup once more. So we had 9.5 going through the wires on it. And we're going to measure this one going through the wires too, just to kind of apples to apples. Why not? Why not? This is the best part of the job, is just testing everything in 100 different ways. All right, so through the wires on this, apples to apples. Boom. All right, 18 milliohms there. So we're comparing 9.5 to 18 milliohms. Essentially half the resistance for this higher pole count motor than the 2-pole count. Now, what's the implication of this? Essentially, a motor that has a lower resistance is going to make more power. All things equal, at least. Because when you have lower resistance, you can pull more amperage for the same voltage applied. And that's the brakes. That's how things work. There we go. So what I'm going to test next is a Puller Pro in a 540, not the stubby, but the 540 size. 2700 kV, just like the rest. And we'll see. So the Revolver had practically half the resistance of the 2-pole. Let's see how it is compared to the 4-pole. Now, admittedly, this is a much larger motor. Much heavier. Let's just go through the wires. So we were at 9.5 and what was the other one? 18 milliohms through the wires, of course. And this one, there we go. You gotta make sure that the leads are on there real good. A lot of pressure. There we go. Ooh, 11.9 milliohms. So extremely low resistance. You know, it's the exact same size as the 2-pole, but it's 60%, about 40% lower resistance or so, just off the cuff measurement. This is one of the reasons why 4-poles are so much more powerful than 2-poles. You may have noticed lately that drag racing crowd has gone from 2-poles to 4-poles. I believe that part of the reason why it took so long for people to realize that 4-poles could actually net them faster times is that you're still limited by traction in a system. I think that's really the biggest limiter in most of these drag race cars, is that it doesn't matter if you can make more power if you can't hook up. If it's not controllable power, or if it's simply more than the tires can handle, then it's just not going to hook. So it took long enough for people to get extremely good at rig setup, at what do y'all call your drag racers? Probably not rigs. And now that people are getting faster and faster, now they're using bigger and bigger motors. So again, 2700 kV. This is the stubby version. So we were at what, 11 and a half milliohms for the standard or so. I forget. You can go back on the video and look. I should have been making notes, I guess. And we're going to measure on the leads to keep this consistent, not up on the solder tabs. The stubby does use slightly thinner wire on the motor leads because it doesn't need to pull as much. All right, so this one's a little higher. We're at 20 milliohms as compared to the 2-pole, which was what, 18.5. Little bit more resistance, but again, we've got the wires in the middle of the path. Let's go straight to the tabs here. Yeah, 17.7. So that tells us very similar resistance, at least between the 2-pole and the stubby 4-pole. You can see that the stubby 4-pole is actually a smaller motor. It's lighter. The 4-pole advantage allows us to have a smaller, lighter motor and produce the same amount of power and torque. That's what that tells you with the similar resistances. Now, motor topology, efficiency at certain RPMs, it does kind of muddy the waters. It's not quite so cut and dry, but that's at least what we can pull from this information, is that higher pole count motors tend to have a much lower terminal resistance, and because of that, they make more torque and power. Now, again, 2700 kV. This is the Puller Pro 540L. This is our R version. This is our race version. The 6000 kV of this is what drag racers have caught on to. It's a massive motor. Let's see how the massive motor tests. So our stubby was about 20 milliohms. Our standard was, let's see, 11.5 milliohms, I believe. May have to go back and test it. Should have wrote it down. And let's see what this is. Through the leads, like the rest. This one has thicker leads. It's a bigger motor. It will pull more torque. It needs thicker leads. That's why I put thicker leads on them. All right, so we're passing 1 amp. We're still passing exactly 1 amp. Okay, we've drifted a little bit. Technically, I should remake some of those measurements, but we've only drifted, you know, 0.1% or something. So it's really not that big of a deal, but just something to keep an eye on. Any current controlled device is going to tend to drift a little bit as temperatures change. All right, so we're testing this at the motor leads, and this is 9 milliohms. So lowest yet. This is the lowest one through the leads that we have on the table. It's only a 4-pole, and it's only slightly less resistance than this 10-pole. And as you can see, there is a huge size difference between them. Now, if we're running the same sort of power levels, the 4-pole is going to run much cooler, number one, because it is a lower pole count and they tend to be more efficient at high commutation rates in general. But it also, you can see how much more case there is. This larger motor, even if it's pulling the same amount of wattage as the smaller motor, it's going to run cooler just because it has more case. There's more motor for that heat to spread out on. There's more motor for the heat to leave the motor from. So that's one reason why outrunners tend to run hotter than inrunners, is that for the same resistance, the same power or torque density of a motor, that there's just not as much place for heat to escape off the outrunner, so they do run hotter. And again, smaller motor, smaller thermal mass, they're going to just heat soak a little faster. So there we go. I'm gonna test this one more time just to be sure. We were in, what, like 9? Yeah, we were right at 9 through the leads. Yeah, 9 milliohms. And if we go to our solder tabs directly, 7.4. Wow. 7.4 milliohms. For the sake of my interest, let's just see what 7.4 milliohms would do if we just shoved 10 volts on it. So amps times ohms equals volts. So volts divided by ohms equals amps. We're passing 10 volts. We're gonna divide that by just the resistance of the motor. We're ignoring our battery and our ESC resistance right now. But that was what, 7.4 milliohms, so 0.0074. Yeah, if you pass 10 amps through this and your battery could take it, 10 volts through this and your battery could take it, and we're assuming again no battery resistance, that's 1351 amps. It's a beefy motor. The motor that has twice the resistance, the 2-pole, it would be half of that. Of course, it's also a shorter motor, but I digress. It would only be able to pull half the amps because it has twice the resistance from terminal to terminal. This is the sort of things that we can gather from the information. But what I really wanted to show is that as we got longer from stubby to standard to 540L length, our resistance went down. It was, let's see, I should have written them down. Totally should have written them down. We can go back and look, but it was about 20 milliohms, and then it dropped down to what, 16 milliohms on the terminal, and then it was 9.5. Oh, it was 9 on the terminal of this really long one. I'm gonna pull out the standard real quick. Just one more time. One more time. Bear with me here, folks. There's the standard. These are all the same, 2700 kV. That makes it easy for us to compare. But again, you know, we were at 1,300 amps that this guy would pull on 10 volts if, assuming the power supply was stiff enough. Most batteries aren't going to be, but I digress. And we could add in, you know, the ESC resistance is most ESCs are going to be about 2.5 milliohms these days for 10th scale brushless one, and then most batteries are going to be, if I remember correctly, for crawlers about 15 milliohms. So the actual resistance of the system is going to add up to more than what this is generally. So your motor isn't really the biggest limiting factor. It's usually your battery. All right. So we were at 20, and then that was for the stubby. For the standard, which is a bigger motor, we're down at 15. Yep, pretty much right on the nose. And then for the longest motor, we were right at 9. So I know the stator sizes, and that's actually exactly how it should jump between them. But bigger motor, lower resistance, it will pull more amps, it will make more torque. It'll just be generally more powerful because, as you see here, bigger motors have lower resistance. These are all the same KVs, so we can just kind of make some base assumptions. We can throw some of the complexity aside by comparing equal KVs. So there you go. I hope that wasn't confusing. I hope that you understood what I was trying to illustrate here and that I illustrated it well and simply. But just to recap here, we used the Kelvin wire setup to measure the resistance of these motors to an extremely high detail with very cheap equipment. As you saw, it was repeatable over and over again. The only drift that we saw was a little bit of amperage on this that was easy to reset. And this illustrated perfectly that bigger motors have lower resistance, and that also higher pole count motors can have lower resistance. I should say. But yeah. I think that was a good illustration. If you do have any questions, please be sure to leave them down below, because this is something that is really fun for me. I really love these tech-heavy sort of situations. And any questions on this, I will absolutely be glad to answer. Look back to the other video for more details on the Kelvin wire setup for first Baron Kelvin and his invention back in what was it, 1861 or 1864. This has been around a really long time. The fact that people way back then in the 1800s were able to have, I don't know if it was current controlled power or if they just measured by, I'd have to look into that. I'm kind of interested now in how they managed. Oh, I'm missing a piece of this. How did they manage to know exactly both the amperage and the voltage back then? I don't know what sort of equipment that they were all working with. So kind of an interesting aside for me. I'm going to look more into first Baron Kelvin's shenanigans. And I mean, he seemed like a very well-to-do guy. I think he lived into his mid-80s, which for back in the 1800s is that's a pretty good run. That's a pretty good run for back then. Even for today, honestly, I'll be happy if I make it to my 80s. Yes. All right. Oh, I forgot to. I got to test this wrench. Yeah. Sorry, that's not the end of the video. Let's test the resistance of this wrench. We need to go totally from end to end. Oh, let me turn this back off. We're going to test the end-to-end resistance of this wrench, because it's very pertinent to what we're doing today. All right, so I'm gonna go right next to these clips on the ends, because as we get closer and closer to the middle, here, let me get this so you can see it again. As we get closer and closer to the middle, our resistance is gonna go down, and I can actually show you that. You know, it's like having a shorter wire. The shorter the wire, the less resistance. All right, so this is showing 0. We also drifted a whole bunch. Now we're at, 0.993 amps. But the resistance of this wrench is, this is saying 0 volts being dropped across this. So we have met our match on the resolution of this. It won't quite do it. So what do? We need more resolution. I'm going to turn up the amps. We're going to go to 2 amps. We're going to get double the resolution. And hopefully we're not going to have a fire. All right, 2 amps. You can hear the fans kicking up speed. Come on now. 0.1 milliohm. It doesn't have a high enough resistance. I mean, it's just a hunk of metal that I'm trying to test here. Let's boost it. We're going to 3 amps. We need more resolution. Mm, 0.2. We're at 0.2 milliohms here. So yeah, it's really low. 3 volts, 0.2 milliohms. We're still not even at 0.1. It's like a third of a milliohm. 0.0003 milliohms for this wrench. Again, if we had a 10 amp power supply, we could go even higher. Of course, these leads would get hot at 10 amps. We would definitely need to be quick about it, so to speak. So yeah, this had lower resistance than I thought because it's just cheap hot metal, but interesting. We were still able to measure something at least. So there you go. All right, I'm done. I swear there's nothing more here that I want to test, and I'm seeing a bunch of stuff that'd be fun to test. Maybe we'll do that another day. The old I'll make a backpack Kelvin wire testing device. I could actually make one that was portable. That'd be kind of cool. Not that I need one, but whatever. If that's something you want to see, let me know in the comments. Do you want me to make a portable, like a battery powered one? You can plug in a 3S LiPo and test your devices. Let me know in the comments. I will actually build one. I do have enough material sitting around that I could. So yeah, there we go. All right, I swear I'm really done this time. Leave your comments down below if you have any. I hope you enjoyed this particular video on Kelvin wire testing of resistance. As always, thanks for tuning in. Have a great day.